We know that capacitors are useful for storing energy, similar to electric batteries in that sense, but they are able to discharge their energy much faster than a battery. Throughout this derivation of the amount of energy stored in a capacitor, we will always remember and apply that the Q on each plate at any time is equivalent to the capacitance times the voltage across the plates. You've seen already this microscopic picture of electrons flowing off of the top plate of the capacitor as they feel the high voltage of the positive terminal of the battery. The battery pushes them out, the negative terminal, and they accumulate on the opposite plate. In this way, an electric field is developed between the plates of the parallel plate capacitor. To determine how much energy is stored in the capacitor, you need to compute the amount of work which is required from the battery to add the next amount of charge, dq, to each plate of the capacitor. Remember, when we talk about charge of a capacitor, we're referring to the magnitude of the charge which is built up on either plate. Of course, the signs are opposite, but the magnitudes are equal. The entire arrangement must remain neutral. Each incremental dq that gets added to a plate will require an amount of work, or potential energy, which is the voltage at that time, times the charge you're adding to the plate. Well, the voltage at the time is just Q over capacitance. So the total work done by the battery will be the integral sum of those small infinitesimal amounts of work, dW. We have the integral of 1 over capacitance, dq q in the integrand. Over the entire charging process, you're going from an initial Q of 0 on each plate to the final Q, which is capital Q value whenever we stop at the fully charged point. So you can see this integral of Q will give a 1/2 Q squared. We'll evaluate at the upper limit and subtract the value at the lower limit, which just gives 0. So the external work, which is required from the battery, is 1/2 Q squared over C. We know that the external work done by the battery is the opposite of the work done by the electric field in the wires during the charging process. But from our work-energy relationship, that electric work is equivalent to the negative delta U during the charging process. There was no potential energy stored initially, so that's 0. And we get that the negative final potential energy is equal to the work done by the electric field. We calculated the work done by the battery here, work external, to be 1/2 Q squared over C. Therefore, the work done by the electric field is negative 1/2 Q squared over C. These negatives cancel out, and we're left with the stored energy in a charged capacitor, final potential energy U, is 1/2 Q squared over C. Now there are 3 equivalent expressions for the stored energy. You're just using different pairs of known quantities. So if you're in a situation where you don't know the voltage and you need to know the stored energy, you'll go 1/2 Q squared over C. If you don't know the charge on each plate, you'll use 1/2 CV squared. And if you don't know the capacitance, you'll use 1/2 Q times V. Of course, the units of energy must be joules, and you can see that Coulomb squared over farads now are equivalent to farad volt squared, which are both equivalent to a Coulomb volt. And as we've seen earlier, the farad, by the capacitance, the definition of capacitance is how much charge we can store on a capacitor per unit of voltage applied to it. So we'll use this stored energy equation a lot. Here's the derivation.